optomechanics, and after the introduction I just want to focus first on the classical dynamics of these systems. So that's the usual procedure. If there is a meaningful classical limit, first discuss the classical equations of motion, then try to discuss the quantum vision. So I want to start by writing down the classical equations of motion. We wrote down a part of the quantum mechanical Hamiltonian, but we can really easily write down the classical equations of motion, including all the damping parts, for example, including the fact that photons decay and that the mechanical oscillations decay. So the classical limit simply means for me that we replace the operator x by a classical variable x. It's more difficult for the light field, but not really that difficult anyway, if you know about coherent states. So in coherent states, which are the most classical states of the harmonic oscillator, you would replace the operator a by a complex amplitude alpha that you can identify, say, with the complex amplitude of the electric field inside the optical mode. So the equations we are going to write down will be equations in x and the light field amplitude alpha. We start with the mechanics because that is simple enough. First I write down the equation of motion of a simple damped harmonic oscillator, and then I add to that the radiation pressure force. So the left-hand side describes the free damped harmonic oscillator, and then we have the radiation pressure force, and we already discussed that in the quantum limit that was given by the energy of one photon divided by the length of the cavity times the number of photons. And now if you are in a highly excited state with a large complex amplitude alpha, then you can replace a dagger a simply by alpha squared. Okay, so this is the mechanics. Now for the light mode, let's first try to write down the part that does not depend on dissipation. And that is something which we know in principle, because we know, for example, what is the equation of motion for the operator A, and that directly translates into the equation of motion for the complex amplitude alpha of a coherent state. So that would simply tell you that alpha rotates at a frequency which would be the optical frequency. So what is the optical frequency? Well, in our case it would be the bare optical frequency times this extra factor that takes into account that we couple to the mechanics. So that would incorporate the fact that the light field oscillates at this frequency and the frequency can change in response to a displacement. Now we have to add two terms, and that is taking into account that photons decay and that there is a laser driving the whole thing. Now, it's not so difficult to write down, phenomenologically at least, even without derivation, a term that would introduce some damping. So then you would write alpha dot equals some decay rate times alpha. So now we already defined a decay rate that was kappa. Kappa was the decay rate for photons to leak out of the cavity, so it would be the decay rate for the intensity. Kappa would be the rate at which the intensity alpha squared were to decay. If you have irradiated the cavity and then you switch off the light beam and then you look at the decay. So if alpha squared goes like e to the minus kappa t, then alpha should go like e to the minus kappa half t. This is something which we had several times, for example, when we discussed dephasing. And so here, the correct decay rate would be kappa half. That's the rate at which the amplitude decays. Now with respect to the laser drive is simply some constant extra term here, plus an extra time dependence, because it oscillates at the laser frequency. Now, I could simply write a constant here, but let me rewrite the constant already in a way that is suitable, introducing some parameter alpha max, which I will discuss immediately, and then I have to keep the time evolution, and the time evolution would simply be an oscillation at the laser frequency. Okay, so why did I choose to write things down like this? Well, you see, if we go through the calculation and eliminate this fast oscillation, then we will see that at resonance, right at resonance, alpha would settle down to a value of alpha max. So I characterize the amplitude of the laser simply by giving the amplitude of the light field inside the cavity when you are driving at resonance. And of course omega L would be the laser frequency. So again, this is nothing but a driven and damped harmonic oscillator. Now there's one step which one usually takes at this point, namely, we want to get rid of these fast oscillations. It would be much nicer to have an equation which is time independent. And that can be done. And it can be done simply by going into a rotating frame. So I want to write my solution alpha of t as e to the minus I omega lt, this is factorizing of the fast oscillations, times some new complex amplitude alpha, which does not any longer contain these fast oscillations. And so then I will insert this ansatz into the equation, and I will find that when I apply the time derivative, I will obtain omega L as a prefactor. And the omega L on the left-hand side cancels a part of the optical resonance frequency on the right-hand side up to the detuning. That's the idea. And afterwards, I can divide out the oscillating phase factor from all over the equation, because here it occurs naturally in the laser drive, and in all these terms it also occurs according to the ansatz. And so if I do that, if I've done that, then in order to simplify notation again, I will rename alpha nu into alpha. So the alpha we will be talking about from now on will already be the one where we have factorized off the fast oscillations. And so I can write down the equation that what would be alpha dot equals, now remember the detuning delta we defined as omega L minus the optical resonance frequency. So because there's a minus omega optical, I will get a plus I times delta. And now there had already been a plus I times x over L. Okay. So this is the first term, just taking into account that I have subtracted off the laser frequency. And then there's the decay, which does not change, plus the external driving, where I can now omit the fast oscillations. So this is really the equation which we want to solve. So now, just as an aside, what would happen if I didn't have this coupling to the mechanics? If I just had an empty cavity that does not have an oscillating mirror, then what's the correct solution? So then I would have to solve alpha dot equals I delta alpha minus kappa half alpha plus kappa half alpha max. And you see that the decay term will always lead to a solution that in the end has alpha dot equals 0. It will relax to some steady state value. The steady state value will not be 0 because of the driving term alpha max. So I can simply solve this equation alpha dot equals 0 for the steady state value, and I will find that alpha bar, the steady state value, equals, so I want to bring this to the left hand side, I have kappa half alpha max divided by kappa half minus r delta, or in other words alpha max divided by 1 minus I delta over kappa half. And in particular, this confirms the notation in the sense that if I set the detuning equals 0, then alpha equals alpha max. So right at resonance, I obtain the right amplitude. It also contains the fact that if I were to plot the amplitude, the intensity of the light circulating inside the cavity as a function of detuning, then I simply would see a Lorentzian. With a height given by alpha max squared and a width given by kappa. Plus there is some phase factor involved which can be read off from this complex number. Okay. That's nice. So now in principle, for example, in order to analyze these systems, you could put these equations, which is just a coupled system of differential equations, on the computer. You could try solving it for some choice of initial conditions and observe the light field dynamics and the mechanics. And depending on initial conditions and your choice of parameters, you would stumble on a lot of different parameter regimes and quite interesting behavior. So in order to simplify things, we now have to be modest in the beginning, and the first thing we want to do is just to imagine that the coupling between the light field and the mechanics only leads to small deviations around equilibrium. So what I'm going to describe now is what you might call linearized dynamics. You solve for the steady state, and then you linearize around the steady state and ask for the solution. And what this will tell us is something very important, namely it will tell us that the mechanical behavior will be modified by the light field, and it will directly lead us to the effects that I discussed qualitatively before. For example, the light field will induce some extra damping for the mechanics, and also the light field will induce some extra frequency shift for the mechanics. And all of this can already be read off from the linearized dynamics. So before I start to discuss the calculation, I just want to point out that what we're going to do is something very generic and very general. The idea is you have some system. In our case, this would be the mechanics. And it's coupled to some environment. This could be a thermal environment, or bath, but in our case it's even a non-equilibrium environment in the sense that it is the driven optical cavity. It is out of equilibrium. And very often it is very useful to reduce the description again to the degrees of freedom of the system, and then you will find a modified dynamics for the system. And one typical example would be a particle that travels through a crystal lattice and that distorts the crystal lattice. And because it does so, it acquires, for example, a different mass. So that would be the example of a polar one. The same even happens to a free electron when it interacts with the electromagnetic field. So we want to try and look at the same kind of effects only for the mechanical system interacting with the optical field. And so the idea then is to somehow eliminate the light field dynamics. The general scheme is always the same. In principle, you can always imagine that you just solve the light field dynamics or the equations of motion of the bath in terms of the motion of the system, which you do not yet know. But suppose you were told the motion of the system, you could solve the equation for the bath. So in our case, this would mean that the light field amplitude at some time t would actually depend on the full trajectory of our mechanical system at all previous times. It turns out that in this kind of system you can even write down a formal solution for the light field amplitude at any given time t, but it contains x of t at all previous times in a nonlinear fashion. Now we want to do things a little bit simpler. We just want to solve the linearized set of equations of motion. We assume, for example, the coupling here is weak, so the effects on the system are not that strong, so then we can linearize. So the linearized dynamics we are going to discuss will work in the following way. We set alpha equals some steady state solution of the kind that we discussed just now, plus some delta alpha. And again, x is the steady state solution plus some delta x. And what will be the goal of this exercise? Well, I told you that the dynamics of the system would be modified by the coupling to the bath. And one way to observe this effect is to imagine that you apply some external force onto your system. Because then you will see that the system, for example, has resonances at slightly shifted frequencies. This is one of the effects. Or for example, in this case, if you were to apply a force to your particle, you would observe that its acceleration is slightly smaller than expected, and this is because it has acquired a new effective mass. So the goal will be to look at the light field induced changes in the response of our system to an external force. So, okay, what are the steps? And this is completely general. First, you solve for the steady state solution, alpha bar and x bar. That should solve the equations where alpha dot and x dot vanish. You have the time independent situation. this is already not entirely trivial because the equations of motion are nonlinear in alpha and x. But for the moment, let me skip that part. Let us just assume that we know alpha bar and x bar. And then let's look at what happens afterwards. So now we want to look at the first order parts of the equations. For example, let's look at the mechanical equation. Now the left-hand side is easy because it was linear anyway, and so if I split x into x bar and delta x, only delta x will remain if I keep the first order. The right-hand side is less trivial because it contained the radiation pressure force. That was h bar of omega optical divided by L times alpha squared. And now I have to take the first order of alpha squared. So that will be alpha bar star delta alpha plus alpha bar delta alpha star. Yeah? So that's the first order if I expand. Now that's the equation of motion for the mechanics. The equation of motion for the light field again has parts that are very simple. Delta alpha dot equals I times delta plus the shift of the resonance frequency induced by the displacement times delta alpha. And now you see, if I want to keep everything to first order only, then I should multiply x bar by delta alpha, obviously. Yeah. So x times alpha to first order contains the term x bar times delta alpha. But it also contains another term, namely delta x times alpha bar. And then I have the decay term, and after that there's no other term. So the driving vanishes because the driving has already been taken into account in finding the steady state lowest order solution. So the driving does not appear in the first order equation. Okay. So now what will be the strategy? The idea is to eliminate the light field dynamics and then to plug the solution into the equation of motion for x. And if you have a look at the light field dynamics, it's an equation that is linear in delta alpha, but it is inhomogeneous because there is a driving term. That's the term here. And the driving is proportional to delta x. So I will eliminate delta alpha in favor of delta x. I will write delta alpha as something times delta x. And then I will insert that up here. So on the right hand side I will also get a delta x dependent term. That's the idea. Okay. So one final step. In the end, we really want to solve for the response to some external force f of t. So that I just want to add here. Okay. So just as an abbreviation, let me call this prefactor, that is the detuning plus something that depends on the average shift, some delta bar. It's an effective detuning which is slightly modified by the fact that the mechanics has already been shifted due to the light force. And so now, what's the best way of solving this equation? Obviously it's going into Fourier space. Because it does not depend on the time, it's linear, so I go into Fourier space. If I go into Fourier space, I will bring all of the terms that involve delta alpha to the left hand side. So that in particular is a term minus I omega from here. minus I delta from there plus kappa half. So that is all the terms on the left hand side. Equals the driving, so to speak, which is provided by this term. Okay. So now, let me just introduce some notation. I want to call this a susceptibility, or the inverse of a susceptibility, in the sense that later I want to write delta alpha equals this times the inhomogeneity on the right hand side. So let me call that a susceptibility chi C, and the C stands for the cavity, because it's obviously only connected to the cavity. It includes the detuning, and it includes kappa, the decay rate of the cavity. So that means overall I get delta alpha of omega equals this susceptibility times the right hand side. Well, and that's already pretty good. Now, if I want to insert this solution into the equation for delta x, there's a slight complication, namely that I have both delta alpha and delta alpha star, the complex conjugate. So that's not really a big problem in time space, but obviously I also want to solve this equation in Fourier space. So what I will need is the following. If you take the Fourier transform of the complex conjugate of some function, then that is actually the Fourier transform itself, evaluated at minus omega, and taking the complex conjugate of that. Yeah, so that's the Fourier transform of the complex conjugate of the function. That's the complex conjugate of the Fourier transform of the function evaluated at minus omega. For delta x, there's no complication, simply because delta x in time space is real valued. So the Fourier transform of that is the same as the Fourier transform of delta x itself. So now let's then try to write down this first mechanical equation in Fourier space. On the left-hand side, we already know basically, because we did the same calculation when we discussed the susceptibility for the fluctuation dissipation theorem. So here I would simply have minus m omega squared plus m times the resonance frequency squared minus I m gamma omega as the damping. And all of this I just identify as being the susceptibility, inverse susceptibility. Now what is on the right hand side? Well, there's the external force, that is simple, plus extra terms. Now let's first focus on delta alpha itself. There I would have to insert delta alpha of omega. That's these terms. There's a constant prefactor which will combine with the one up here. There's the susceptibility of the cavity evaluated at omega. And there's delta x of omega. So let me write the delta x to the far right, because there will be another term of the same kind of structure coming from the delta alpha star. So if I multiply these terms, I get an I, an h bar times optical frequency over L squared, plus alpha bar times alpha bar star is simply the magnitude squared. Okay, so now for the rest of the terms. Here I would get a factor chi c of omega that enters here. And now comes the tricky part. Delta alpha star Fourier transformed would be obtained by taking the Fourier transform at minus omega and the complex conjugate. So I have to look at this formula and insert minus omega and take the complex conjugate. Taking the complex conjugate will turn I into minus I. Yeah. So that gives me a minus sign. I also have to insert minus omega and take the complex conjugate of the susceptibility of the cavity, and that's important, that's non-trivial. And then I have to insert, well, delta x star of omega, but that's really the same as delta x of omega. So that's not tricky, and I can pull that factor out. Okay. So now we have achieved what we wanted to achieve, or almost, because we have something which only involves delta x of omega and the external force. Now I just have to insert some abbreviation. So all of this prefactor I will call k of omega. And then what I find if I solve this equation is simply delta x of omega equals, and now this is the final result, so to speak, f of omega, the external driving, divided by the inverse mechanical susceptibility minus k of omega. So for example, if k vanishes because I don't couple to any light field, then I divide by the inverse susceptibility, or I could as well multiply with the susceptibility. And I would be back to the usual mechanical linear response. Delta x equals susceptibility times force. Yeah? Only because of the presence of this light field induced changes do things look more complicated. And so if I like, I can say, well, this is f of omega multiplied by some effective susceptibility. And that is defined, obviously, as being the inverse of this denominator. Okay, so the next step will be to discuss the meaning and the consequences of having this extra term k of omega. And the first thing I want to point out is that this structure is very general and appears in many other contexts as well. So you have a system or a particle that couples to some fluctuations, to some environment, its properties are changed, and in quantum mechanics usually instead of talking about the susceptibility, about the linear response, we would first try to calculate the Green's function of the particle. And then it turns out that the Green's function can always then be written as the inverse of the inverse bare Green's function minus something which is called a self-energy. So this is just an aside. So the Green's function would look like the bare Green's function, let's call it G0, inverse minus something which people call a self-energy. And again, you see if the self-energy vanishes, then you just get G equals G0. But if there's a self-energy, why is it called a self-energy? Because it will turn out that if you analyze it more closely, that this leads, among other things, to a shift of the energy of the particle. And so, in our case, we're talking not about the energy of a particle, but we're talking about a harmonic oscillator. And we will see that this k of omega directly gives you a measure for the frequency shift of the harmonic oscillator. Okay. Well, so how do you obtain the meaning of k of omega? How can you tell what it means? In general, it will be relatively hard, but we want to assume that the coupling is small, or in our case, that the light intensity is small. If the light intensity is small, capital K is small, so it will be a sort of small correction, and then we can more easily interpret it. And the best thing is to look in the vicinity of the resonance. And in the vicinity of the resonance, I can say the following. Look at the structure of this first term that appears in the denominator. The idea will be to compare term by term, to compare the real part and the imaginary part, in order to learn the meaning of the real and imaginary part of capital K. So the imaginary part of this will be minus Im gamma omega. And since we are near the resonance, I will allow myself to set omega equals to the resonance frequency. So that is minus Im gamma omega. And now what does that mean? That means if there's an imaginary part to capital K, then this imaginary part will have the meaning of an extra damping up to some prefactor, but I can read off the prefactor. So what happens if I were to enter a delta gamma here? Well, then I can see that up to this prefactor, that must be equal to the imaginary part of K. So let's see, the imaginary part of K evaluated at resonance would be equal to plus M omega times a change in the damping rate. Why is it plus? Well, because there's already a minus sign in front of K, and there's a minus sign in front of K. Or in other words, the delta gamma, the extra damping, which I want to call gamma optomechanical, equals 1 over M omega times the imaginary part of K. There's something similar for self-energies. There people learn that the imaginary part of the self-energy directly gives you information about the extra damping induced by the coupling to the environment. So this is one part. I also promised that there will be a frequency shift. So that then presumably is connected with the real part, and I want to take the real part of the susceptibility near the resonance frequency, and I find this would be, well, m times capital omega squared minus omega squared. Now this can be written as sum times the difference. And in the sum of capital omega and small omega, I can just replace small omega by capital omega. So that is 2 times the omega and then the difference. So now what happens if I change the resonance? If I want to shift the resonance, I simply have to insert a change delta omega in here. So that means automatically delta omega will be 1 over this prefactor 2m omega times the real part of k. And more precisely because of the negative sign in between the two, there's a minus. So these are the 2 important equations that we obtained. These equations, so to speak, tell you what is the meaning of capital K. The imaginary part gives the extra damping, the real part gives the frequency shift. And so we are basically done. All that remains to be done is to evaluate these and to discuss them, for example, as a function of the detuning, which enters as an important parameter. Okay, are there any questions at this point?
From these final results, I cannot see why you make an assumption for small aerorated density.
Oh, yes, because you see that I take the liberty of setting myself right at the resonance frequency. Now, if I crank up alpha squared and k becomes larger, then of course there will already be a frequency shift, and so the resonance frequency has already shifted. And then I would have to self-consistently evaluate k at the shifted resonance frequency. And so at some point it becomes questionable what is the correct interpretation. But for small coupling I can always take the bare resonance frequency. So that's the idea. Yeah. Otherwise, still qualitatively it's always correct to interpret the imaginary part as having something to do with the width of the resonance, the damping rate, and the real part to have something to do with the shift of the resonance. But if the coupling becomes stronger, you can see effects that are quite more complicated. For example, at some point, you could even have 2 peaks appearing instead of 1. So the 1 peak can split into 2. All of this is contained in this formula. So, in order to discuss these formulas, let me first introduce some abbreviation. Because there was a certain combination appearing in the prefactor of all of this. So we had the frequency divided by the length of the cavity squared times the light intensity times a prefactor which turns out to be h bar over 2m omega. But this you recognize, this is nothing but the mechanical ground state. So all of this I want to call G squared. And G is a kind of coupling strength between light and mechanics that in this case depends on the intensity. So later on we will see that it's reasonable to call this the linearized optomechanical coupling strength. And in words you could say G is really, if I take the square root, G is the optical frequency shift per displacement times the 0-point displacement, and then still multiplied by the square root of the intensity, the square root of the photon number. So let me first discuss the effective damping rate. So if I insert the definition and take the G squared, then I find that the optomechanical damping rate is 2 times G squared times the real part of this difference in the cavity response function. So now you can insert the cavity response function and you find that optomechanical damping rate would be G squared times kappa 1 over omega plus delta squared minus, is the same expression but with omega minus delta. Now, this is the expression for arbitrary omega, and then I have to set omega equals the Bayer resonance frequency to find the actual value of the damping rate. Okay, so this is a formula that simply scales with the square of the optomechanical coupling, and in particular is proportional to the laser intensity. That makes a lot of sense. The light-induced change to the damping is proportional to the laser intensity. But then, the important parameters are the detuning, obviously, and kappa. And so I now want to illustrate the result. And so I want to plot everything against the detuning. And so what one finds is that if kappa is small, that is kappa is smaller than the Bayer resonance frequency, then you simply get peaks at minus the Bayer resonance frequency and plus the bare resonance frequency. And the peaks are such that the one minus the bare resonance, that is detuning equals minus the bare resonance frequency, is positive. And so this is really an extra contribution to the damping rate. Whereas the whole function, you can easily convince yourself, is antisymmetric in the detuning. So at plus omega, you get a negative peak. And so, since this means extra damping, we could also say that is the cooling side. Whereas that would correspond to heating. And so at the moment it might be not immediately evident that this should be the result, but we can give it a simple physical interpretation. So if you have your optical cavity here, and you come in with a detuning that is minus the resonance, that means you come in with a laser which has almost the optical resonance frequency, but minus the mechanical frequency. Then typically this laser beam would simply be reflected from the cavity, since it is not at resonance. It's below resonance. But the point is that if there are vibrations in this cantilever, then so to speak, you can absorb a phonon, the light field, the photon can absorb a phonon and thereby be shifted towards the optical resonance, and then it can enter the cavity. And then it will also leak away from the cavity, and it will leak away blue shifted, in the sense that it has gained some energy. Exactly has gained the energy that the cantilever has lost. And so this is cooling. And if you think about it, this is just a version of Raman scattering. If this cantilever were a molecule, for example, you go in with some frequency, the molecule has some vibrations and can add this frequency to the light beam. Okay. And of course, for positive detuning, you carry some little extra energy in the light field, and this extra energy will be dumped into the mechanical motion, and that is why you get heat. So this is the result if kappa is much less than the mechanical frequency. You can also evaluate this if kappa is actually much larger than the mechanical frequency, and what happens then is that you get a far broader peak, and the maximum roughly sits at kappa. I mean, here it sits at minus kappa, and there it sits at plus kappa. So in this field there is a name for the regime where kappa is much less than the mechanical frequency. It's called the resolved sideband limit. And the reason it's called the resolved sideband limit is fairly easy. So if you illuminate the cavity at a particular laser frequency, then you get back this blue shifted part of the beam, for example. It's shifted by omega. But if kappa is much less than omega, then the broadening of the beam will be small enough to be able to resolve this sideband. So there you have a situation where the coupling of a mechanical system to some environment, in this case a non-equilibrium environment, can give rise to both cooling and heating, depending on the details, depending on the detuning. Okay, so much for the damping, but it's also interesting to have a look at the frequency shift. Okay, so if you plug in the equations we had before, then it turns out the frequency shift also has a simple expression. So delta omega would be minus g squared times the imaginary part of this difference, which we already discussed. And again, I would have to insert frequency equals the resonance frequency. And so let me plot this as a function of the detuning. Again, the function is antisymmetric in frequency. And let me first plot it in the case where kappa is really much larger than the mechanical frequency, and it simply looks like this. So physically, what does it mean? If delta omega is larger than 0, then obviously the spring gets stiffer. The light field stiffens the mechanical spring. And conversely here, it gets softer. So in this limit, if kappa is much larger than the mechanical frequency, you can also have the picture that we discussed in the very beginning of a static extra potential being added to the harmonic oscillator potential. You remember the picture where I drew several local minima, and then each of these minima will have a curvature that deviates from the intrinsic curvature of the mechanical parabola. And so that is exactly this effect. Now there's an interesting side note here. We said that negative detuning belongs to cooling. Cooling is often what you want to have. Unfortunately, it also leads to a softening of the spring. Now this is usually not a problem, but if you really turn up the laser intensity to make the spring, to cool harder and harder, then you also make the spring softer and softer, and there's a danger here. Because at one point you will come to a point where the overall potential no longer has a positive curvature but has a negative curvature. So you have a completely unstable situation. And then the particle will not stably sit at this position but will slide to either side. And so you will never be able to really fix it at this particular detuning because it will go somewhere else. And that's really been a problem in some of the cooling experiments. So if you turn up the laser power to get better cooling, then you make the spring softer and softer, and at some point you become unstable. Now this can be circumvented really in the case of the resolved sideband limit. So I will now draw the result of plotting this in the resolved sideband limit, which looks a little bit more complicated. In any case, the important features then sit at plus omega and minus omega. And what you see essentially are almost singularities. It looks somewhere like this. And here is just antisymmetric. So what you see in particular is you can choose the detuning right at the negative resonance frequency, and then the cooling will be particularly strong, but the optical spring effect can vanish. And that's a good thing. So you can avoid the instability. So let me just note this. Now, how large is this effect, this so-called optical spring effect? Turns out there have been experiments in which people have turned up the laser power so that they have increased the stiffness by a factor of 100 over the mechanical stiffness. So almost all of the spring was really provided by the laser instead of the mechanics, instead of the suspension of the mirror. And they calculated, so to speak, what would the stiffness correspond to, and it would correspond to holding the mirror with a stiff beam of diamond, so to speak. So it can be a really strong effect. So then let me point out something which qualitatively I already discussed, but here we can come back to it. Namely, what happens if the full damping, which is the intrinsic mechanical damping, plus this extra optomechanical damping, what happens if this becomes negative? So once again, I want to plot now the full damping versus detuning, say in the resolved sideband case, and everything I have to do is take the curve that I have discussed and shift it up by the intrinsic mechanical damping. I'm sorry for the inconsistency in notation. I believe here in the equations I called the intrinsic damping gamma, but maybe it's better just to indicate gamma m as the mechanical damping. Now, how did the picture look like? Well, at minus omega I had extra damping, and at plus omega I had negative damping, negative extra damping. So here there is no problem, I will get cooling, but there is some region obviously where the total overall damping becomes negative. And so that really leads to an instability. And the region of instability can precisely be found from this condition, that the full overall damping rate becomes negative. In all other cases, the system is stable. And so now you can guess what happens if I change the laser power. If I change the laser power, then simply this extra contribution to the damping rate changes. So for example, if I were to make it half as large, the overall damping looks like this. And maybe in this particular plot I chose, I would only have a tiny region of instability left, and if I reduce the laser power even further, then I will have no instability. So that means in the region in the plane of detuning versus power, there will be a threshold in the power at which I get first hint of the instability, and then I will have a growing region of instability. But then, of course, if the instability kicks in, then, as we discussed qualitatively, any small perturbation will blow up. And after that, you can no longer apply the linearized equations. So there you really need to go into the nonlinear dynamics. But in order to find the region of instability, it's good enough to have the linearized dynamics. And that is also a fairly generic feature. Are there any questions left? Well, if not, then I think that's a good point to stop for today. And then see you next week.